Welcome back, Year 10. This is the fourth lesson, lesson 4 of the waves topic. Today we'll be learning about the electromagnetic spectrum, and please write down lesson 4, date, and the title is already in the line for you. Before we begin, let's see where this lesson fits in on the spec. We'll be learning about the term radiation and energy given out by radioactive materials and the different parts of the electromagnetic spectrum and the relationship between frequency and wavelength on the different parts of the spectrum. Also, you can see here you have to be able to name the 7 regions of the spectrum, have knowledge of the order, and we'll be using the fact that the speed of light, 3 times 10 to the 8 meters per second, is the speed of all the electromagnetic waves. That's what they have in common. Anyway, we'll be coming on to that. First of all, quick question. What object do these 4 images show? Well, they all show the sun through different parts of the electromagnetic spectrum. So we have the one part, ultraviolet. We just use UV for short. Infrared, X-rays, and visible light. Now there's 7 different parts of the electromagnetic spectrum, and you're going to use information to answer those 6 questions in a moment. But so what I'm going to do, I'm just going to hold that up in the screen, and you're going to use that information to answer those questions. So before we do that, we're going to quickly look at the video. Once we've looked at the video, you're going to answer those 6 questions.
Shh! Remember my instructions. Visible under X-ray glasses.
What are you on about, Paula?
Remember my instructions. Visible under X-ray glasses.
What?
It's a mnemonic, Alex. A sentence used to help us remember the 7 different types of waves in the electromagnetic spectrum.
Okay, but what is the electromagnetic spectrum?
Right. Well, we know that there's 2 different kinds of waves.
Transverse and longitudinal.
That's right. Well, now we're just going to look at them in more detail, starting with light.
Light? That's a transverse wave, isn't it?
Correct. And a very fast transverse wave. Light travels at 300 million meters every second.
Which is very fast.
And it's not the only one. There's a whole family of waves with very similar properties, and they're all called electromagnetic waves.
Electromagnetic waves. Got it.
Right. Now, the first thing we need to learn are the names of the 7 electromagnetic waves in order.
How do we do that?
Easy. Remember my instructions.
Visible under X-ray glasses.
Yes. Now let's look at the words. R is for radio waves. M is for microwaves. I stands for infrared. V stands for visible light. U stands for ultraviolet. X is for X-rays, and G stands for gamma rays.
Okay, that makes sense, but why are the waves arranged in that order?
The waves are arranged according to the size of their wavelength and frequency.
Oh, I know what this means. If we take a wave like this one, the distance from one peak to the next peak is the wavelength, and the number of peaks or complete waves you get in 1 second is the frequency?
Precisely. Now let's see what the waves look like for each of the 7 types.
So if we look at wavelength, radio waves have the longest wavelength and gamma rays have the shortest wavelength?
Right. And because the changes in the wavelength are so gradual, this is called the electromagnetic spectrum.
Use this information then, and what you've learned in that video, to answer these 6 questions. So you need to pause the video on that information, have your booklet open, and then answer those questions. This will be a self-assessed question, and I'll go over the answers with you once you've finished. So pause now, please. Okay, I've written down now the answers. So I want you to compare your answers to what I've written down in red. Correct and add 2 as required. I'm going to try and fit in all 6 answers there. So you need to pause and check your answers, though I will go through each of them. What are electromagnetic waves? They're transverse waves as opposed to longitudinal, and they all travel at the speed of light, which is, and I'll add that in, 3 times 10 to the 8 meters per second. Remember, nothing travels faster. That's 300 million meters per second. What do these waves transfer from one point to another? Important point to remember, they all transfer energy. It could be light energy, heat energy, different forms of energy. What do these waves, question 3, how do these waves differ from each other? They differ in terms of their frequency, the wavelength, and their amount of, missed a word there, amount of energy. How fast do electromagnetic waves travel through a vacuum? I just mentioned a moment ago, it's 300 million meters per second, or 3 times 10 to the 8 meters per second, which again is the speed of light. Nothing travels faster. 5. Explain what a vacuum is and why it's important that light and infrared waves can pass through a vacuum. So 2 questions in one, 2 for the price of 1. So firstly, a vacuum is a space with no particles inside it. Light and heat, which is infrared, reach us via space from the sun. Life would not exist if they couldn't travel through a vacuum. Question 6, finally, we cannot detect most of the electromagnetic spectrum. Name 2 waves we can detect and name the sense organs used. Light detected by eyes, heat, and again, that's infrared. I'll add that in. Often spelled incorrectly. Infrared. Turn over to page 26. It's a blank page, which looks like this. What we are going to do now, together, is draw this, the electromagnetic spectrum, in order to help you remember and learn the different parts of the spectrum and the relationships of the different parts of the spectrum. First thing I'd like you to do is to draw in the middle of the page 2 horizontal lines. And we're just going to use those 2 horizontal lines to draw the whole of the spectrum. Let's try again. Not sure what happened there. And the difficult part is then drawing a wave going from left to right where the wavelength is getting ever so slightly smaller as we go across. And then, as we approach the end, the wavelength gets incredibly small, which is representing the electromagnetic spectrum. Then let's label the different parts of the spectrum, starting with radio waves, microwaves, then we've got infrared, remember the fra, the visible spectrum. Now the visible spectrum is a spectrum, you've got a spectrum within a spectrum, because the visible light is what our eyes detect. That's a part of the spectrum from 400 to 700 nanometers approximately, and it starts off with red, orange, yellow, green, blue, indigo, violet, the colours of the rainbow. And within that you have a spectrum where red is the longest wavelength and violet the shortest. And there's a connection there, isn't there? Infrared, this is an easy way to remember it. And then next to visible light you've got ultraviolet. The V of the violet. Two left, X-rays and gamma rays. X-rays and gamma rays, or gamma waves. Gamma rays. What's the relationship? Well, what have they got in common? All travel at 3 times 10 to the 8. Do that again. 10 to the 8 meters per second. What else can we say? Well, if you go from left to right, let's make it stand out a bit more, different colour. Left to right, that's increasing frequency. And if you go from right to left, it's increasing wavelength. Try that again. Now I'll try and make sense of that for you. What we're saying then is, right, that, remember that's V, that's speed, that's lambda, and that's F. And from previous lessons, remember this, speed is frequency times wavelength. V is constant. So if the frequency goes up, then the wavelength has to come down, or vice versa. So what I'm going to ask you to do next is to draw that again. So pause the video now, so you've got all that information on your page. And at the bottom of the page, I want you to come up with a mnemonic in order to help you remember the order of the waves. Think back to that video, and the lady in the video used her own mnemonic. You can use that very same one. I've added that mnemonic now at the bottom. So that's, remember my instructions, visible under X-ray glasses. The first letter of each word are the same. So R, remember, and radio, M, microwave, and so on. So pause the video until you've completed that. You can use that mnemonic there or come up with your very own. Pause now. When you've completed that, press play. That's quite useful to look at. Okay, you can pause the video in any part of that, which is a summary of what we covered so far. Now your next challenge on page 27 is this. You have 1 minute to draw a rough electromagnetic spectrum diagram like you've just drawn, then answer the 4 questions by circling which you think is the correct answer. Here are the 4 questions at the bottom. Don't worry if it's not exact. Okay, so it will go, you go first, and then I'll go over the answers with you. So don't worry if it's not exact. Think back to what we've just done there. Look at that and see how much you can remember. You're not getting marked in it, so on your marks then you've got 60 seconds. Marks, set, go. Okay, we just fast forwarded in time. That's your minute gone. And these questions. Which is the longest wavelength? Well, what I'd have hoped you'd have drawn would be something like this. That wasn't a very good one, was it? Because it's difficult to get the same amplitude. But in 60 seconds, what more can you do? And then you've got your, again, the radio waves, etc., microwaves, all the way up to gamma rays. As much as you could do in 60 seconds. So the longest wavelength is that direction. So X-ray or indigo. Now indigo is part of the visible spectrum, remember. Perhaps the easiest way to show that is back here. Here's indigo, and there's X-ray and ultraviolet. So indigo would have the longest wavelength. Ultraviolet or infrared. I can look at this one underneath here. You can see long wavelength that way. Therefore, we've got ultraviolet has got a shorter wavelength than infrared. So infrared would be the answer. High frequency. Now with frequency, the further you go to the right, the higher the frequency. So the more you go that way, the higher the frequency. Green or yellow? Well, if you remember, within visible light, here, you've got the Roy G. Biv, red, orange, yellow, green, blue, indigo and violet. Green has got a longer wavelength, has got a shorter wavelength but a higher frequency than yellow. Okay, because remember, and the wavelength gets smaller as you go from red to violet. Infrared or red? Well, red, look, is to the right of infrared, so it's got a higher frequency. Shortest wavelength, X-ray or gamma. Gamma's got the shortest of the lot, so that's gamma rays. It's over here. In ultraviolet or infrared, that's ultraviolet. Lowest frequency. So the further you go to the left, the lower the frequency. So that's going to be microwaves, radio or infrared. The radio's got the lowest frequency of the lot. There. Then on the next page, that's what I've just been scribbling and drawing all over, is another diagram of the spectrum, and underneath you can see some uses of the spectrum. And they've done a neat job there of showing frequency, low frequency down here, high frequency, short wavelength, long wavelength. And underneath, some more information that I'd like you to read through. And when you've read through, answer question 1 and question 2, please. So pause the video. When you've answered question 1 and question 2, press play again. So question 1, what process occurs at point X in the diagram? Well, point X in the diagram here, you can see the light is going from air into glass. It's slowing down. Remember, we call that refraction. We learnt this in a previous lesson. And there's a picture on the right hand side here. It's taken off an album cover, Pink Floyd, Dark Side of the Moon. And it shows a white light going in here and the colours of the rainbow, or the visible spectrum, coming out the other side. Question 2. The table gives the position and reading of each thermometer 10 minutes after the investigation started. What conclusions can you draw from the results table? Well, if you look at the temperature, you've got the highest temperature there at 24, which is a red light. So you could say a red light has the highest temperature. Now that will be because it's next to infrared in the electromagnetic spectrum. Red light has the highest temperature because it is adjacent. It is adjacent to infrared in the electromagnetic spectrum, EM spectrum. To help reinforce what we learned so far, we're going to watch another short video.
Why do we need to know about the electromagnetic spectrum?
Because electromagnetic waves are incredibly useful. Radio waves are used for sending radio signals. That's how you can listen to your favourite FM radio station. And you're also using radio waves to control your radio-controlled car. And as for microwaves...
Everyone knows they're used for cooking in microwave ovens.
But did you know that microwaves are also used for sending satellite signals?
Satellites use microwaves?
Yes. They use a frequency of microwave which easily penetrates the Earth's atmosphere.
And as for infrared, very useful. TV remote controls use infrared signals to change TV channels.
Meanwhile, the North...
And police use infrared night vision cameras in their helicopters.
Visible light. We see things using visible light waves.
True, but they're also used for sending information down an optical fibre.
Optical fibres? Like in my optical fibre lamp?
Exactly the same principle.
And ultraviolet. They use ultraviolet lights in nightclubs.
Yes, and if you're wearing something white, then you'll very easily be spotted.
And can't you spot a dodgy banknote by putting it under an ultraviolet light?
Yes, banknotes have a hidden security mark, which is only visible under UV lighting.
And X-rays are used for detecting broken bones.
And they're also used for detecting broken pipes buried underground.
And what about gamma rays?
Gamma rays are used for killing cancer cells, but they're also used for sterilising things, because they can kill all the bacteria on a plastic syringe without melting it.
So electromagnetic waves are really useful.
Yes, they are really useful, and there's a good overview there. It's shown in this diagram of the applications and uses of electromagnetic waves. Now underneath there's some more information on the gamma rays. I'm not going to read through that, that's for you to read through, and some additional information there. You can pause over this screen, which is really a summary of what was covered in the video and in your booklet. Just add in here, danger very short wavelength. Okay, remember these are the shortest wavelengths and the highest frequencies. They can pass through materials, including our bodies. They can damage and kill cells. They can go through our skin, through our bones. Remember, X-rays can go through bones. And this is, I've just drawn, what I want you to do is just add in what I've added there to this diagram. Sorry, we're at the top of page 30 now. And what you're looking at here, I'll add one more in, is how cancer can be treated using what's called radiotherapy. And those orange circles represent normal cells, and the purple cell there is a cancerous cell. And in radiotherapy, what you're trying to achieve is to kill the cancerous cells. So the cancerous cell can be hit by gamma rays from different angles. So you can see what's happening here. We want to kill off that cancerous cell, but other normal cells will get damaged at the same time. But the important thing is to kill off the cancerous cell, because the cancerous cell can spread and multiply, which should be the start of a cancerous tumour. Underneath then, what I'd like you to do is just to put in your own words an application of gamma rays. So you can use radiotherapy. I'll just write that down for you. You may want to rewind the video in order to help you answer that. Next, we've got X-rays. X-rays you hear about where you can look inside people, because the bones will absorb the X-rays and the soft tissue allows the X-rays to go through. More information there. And in lower doses, it says at the bottom, they can damage DNA. So that's why people who work as a radiotherapist, they need to minimize the amount of exposure to X-rays to avoid damage to their bodies. And as I showed in that video, it can be used to check wells in pipes and general metalwork and look for faults. Now, again, more information there on X-rays. Your homework is this. You can read through that. I've just put some more information there that we've had up above on gamma rays. And what's the question is, look on there's a typo on the internet to explain what ionizing radiation means, what it can do to cells, and what it could cause. If you look at this, I got some additional information as to what you've got in your booklet here. So ultraviolet, again, it explained in the video, it can be used to check for fraudulent banknotes, money. Comes from the sun, and sunburn can be an outcome of overexposure and can cause skin cancer. You can see a nasty case of sunburn there. Now, some ultraviolet light from the sun is absorbed by the Earth's ozone layer. So that's what the ozone layer does. It can absorb some of the harmful ultraviolet rays. You have questions to follow on this. You can see this gentleman here, even though he could be in a cold, he could be, say, in the Alps, So even though it's not particularly warm there, because you're higher up, you've got less protection by the Earth's atmosphere from the ultraviolet rays. So if you're high up in the Earth's atmosphere, for example skiing, then you'll be exposed to more ultraviolet rays. That's why you slap on, remember, sun protection cream. So to illustrate that point in your book, what I'd like you to do is explain by adding relevant information to your diagrams why this skiing pig is in danger of getting sunburn. So that there he is, 500 meters above sea level and sea level there. So this is one way you can add your own annotations. So you've got less protection when the skier is higher up. You've also got ultraviolet reflecting off the snow, because the snow is very reflective, it's white. But when you're down at sea level, you've got many more ultraviolet rays that are absorbed by the Earth's atmosphere. Pause the video, add in your own annotations. Moving on, communications and optics. Electromagnetic waves are used for communications because they travel so fast. They all travel in a vacuum, remember, at 300 million meters per second. Right, to do, unscramble the anagrams and link them to the correct sentence. These are the anagrams, and then you have to put them next to the correct sentence. So for example, if you unscramble that, it's microwaves. Then you go over here and find which one it is for microwaves and write it to the left hand side. Okay, compare your answers now to what I've added in there. And then underneath there's some more questions for you to do, questions 1 to 3. I'll go through these questions with you. I'm not going to write the answers down, you write them down in your own words. Question 1. And you can use that information above. What type of electromagnetic wave do mobile phone masts transmit? Mobile phone use microwaves to send information. Fully explain why some scientists believe children should only use mobile phones for emergency calls only. Well, the skulls of children are thinner than adults, therefore more microwaves could get inside the child's brain. There's no scientific evidence suggesting that children's brains have been adversely affected by mobile phones, or adults in that case. There's no conclusive evidence. But remember, mobile phones in general use have only been around since the 1990s, so what's that, 25 years perhaps, the mid-90s when they were first became really accessible and popular. So the next question, how could the problem of microwaves being absorbed by children's brains be reduced? Well, what you can do is, number one, limit the use of phones. Don't hold them to your ear, so use a speaker function or headphones instead. Once you've completed question 3, then there's information on the next page. I've just copied it to the right hand side on visible light. We've already covered. Now, detectors of visible light, eyes, cameras, and a quick activity here for you to do. Describe how we see objects. Well, light has to go into your eye to be detected. So in order, let's look what it says here. The girl is looking towards a cupcake. The only light source in the room is a lamp. Use all the box words to explain how we see objects. Include arrowed light rays in your diagram to show your explanation in picture form. Okay, you need to draw 2 rays of light because the light is reflecting off. Let's use purple. Too thick. Remember the law of reflection. The angle of reflection equals the angle of incidence. And we use an imaginary line, the normal, to measure those angles. So to use all these words, what you've got to do underneath there is write a paragraph using the words above. So we could, I'll just give you an example. You write it in your own words again. The light source emits light towards the cupcake, which is known as the object. The light reflects off the cupcake into the pupil of the girl's eye, or something similar, words to that effect. When you've completed that, turn on to page 37. Infrared waves. Think back to the video. They looked at a few examples of infrared. Police use it for detecting criminals who are trying to escape in undergrowth and so on. It can be used to detect how much heat is escaping from houses, to see how well houses are insulated. You can read through that. Now, read through the remaining information on page 38 and 39, because that information you'll need to use in order to answer the plenary assessment. That brings us to the end of lesson 4. Again, make sure you go back to study zone and answer the plenary assessment for this lesson. Bye, see you next time. Oh, but listen to this song. That will help you remember the most important learning objectives of today's lesson. Bye.
Gamma rays, X-rays, ultraviolet visible, infrared and microwave and radio waves. Gamma rays, X-rays, ultraviolet visible, infrared and microwave and radio waves. Gamma rays, X-rays, ultraviolet visible, infrared and microwave radio waves. Gamma rays, X-rays, ultraviolet visible, infrared and microwave radio waves. It takes a lot to stop the deadly product that you've got from radioactive decay. Gamma rays are scary, but they used to kill cancers because they've got the highest energy. Gamma rays, X-rays, ultraviolet visible, infrared, microwave, radio waves. Gamma rays, X-rays, ultraviolet visible, infrared, microwave, and radio waves. X-rays are safe enough to use on humans. They go through skin, they're stopped by bone. Ultraviolet light might give you a suntan, but still it's not safe and your skin may burn. Gamma rays, X-rays, ultraviolet visible, infrared, microwave, radio waves. Gamma rays, X-rays, ultraviolet visible, infrared, microwave, radio waves. All of the invisible is easily detected. Just open up your eyes and you'll see it. You need infrared sight for seeing things at night. My remote control is working by heat. Gamma rays, X-rays, ultraviolet, visible, infrared, microwave, radio waves. Gamma rays, X-rays, ultraviolet, visible, infrared, microwave, radio waves. Heating up your dinner or chatting on a mobile, microwave frequency is low. The danger is much smaller, the wavelength is much longer. Now relax with your TV and your radio. Radio waves. Gamma rays, X-rays, ultraviolet, visible, infrared, microwave, radio waves. Gamma rays, X-rays, ultraviolet, visible, infrared, microwave, radio waves. Gamma and an X, ultraviolet, visible, infrared, microwave, and radio waves. Gamma and an X, ultraviolet, visible, infrared, microwave, and radio waves. Gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio waves. Gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio.